Hello, math fans. I'm going to talk a little bit about the concept of a dot product and how really there are so many ways to think about what it is. The key thing is it's easy to compute and it gives us indirect information about the angle formed between two vectors. Ultimately, I think about it as part of this law of cosines, and I want to explain why that is. And then I'm going to do something I haven't done for a long time, which is I'm going to prove the law of cosines. I don't think I've done that since like middle school, high school. And it's always funny when you do something like that, you realize it doesn't really take very long. And so I'm going to end this video by explaining how I went about trying to prove that thing. I was like, there's got to be a quick way we can do this. So we'll talk about how you can do something like that, even if you don't, have it in front of you. How do you think through such a thing? So we'll finish with that. Okay, so I always call this the 10-star fact of dot products. It's the dot product is indirectly connected to the lengths of the two vectors you start with and the angle between them in this way. So if somebody says, tell me what the dot product is, I sort of point to that theorem. Now I can tell you several other things, but let's do that here. So let's say we have this vector A and this vector B, and we have this angle between them. So when we talk about this, we mean they're tail to tail. That angle can be acute, it can be obtuse, but we always mean that smallest angle. So we don't mean go around the long way, we mean the shorter way. So that means it's always between 0 and 180. It's really easy to execute. You just multiply components. So for example, if I take two vectors, and it works for 2D or 3D, and you do their dot product, all you have to do is multiply corresponding components. So 1 times 3 is 3, 2 times 4 is 8. And the weird thing about the dot product is then you add them together. And you get this number 11. And you're left with the natural question, which is, what in the world does 11 have to do with my vectors? And let's use this 10-star fact. I will prove it at the end of this. Let's see what it means in this example. So it tells me something about the angle. So a lot of times the way we use that 10-star fact is we get cosine by itself. So we do the dot product of the two vectors, we divide by their lengths, and then we hit the inverse cosine button. So that's something you're going to do a lot in a 3D calculus course, because any question that says find the angle, this is what you're going to do. You're going to find two vectors that are tail to tail and point out of whatever you're trying to study, and then you can compute this. So the bad part is you have to compute the lengths. This is going to be square root of 5. How did I get that? I found the length of this vector. 1 squared plus 2 squared square root. What's the length of the other vector? You can try that. Square root of 3 squared plus 4 squared. I think that's a square root of 25, which is just 5. And then I made up these numbers just now on the fly, so I'm going to pull out my calculator. I'm going to hit the inverse cosine button. I'm going to do 11. Sometimes students type this in wrong. Divided by 5. And I'm in degree mode. So I've calculated this thing. And what do I got 10.3 degrees. So I'm getting that this is about 10.3 degrees. Is that reasonable? Well, the two vectors I chose was a vector that went over 1 up 2. Which that's a terrible drawing of that. So over 1 up 2. Then I did another vector that was over 3 up 4. So it makes sense to me that the angle between those is going to be pretty small if you think about it. So 10 degrees makes sense to me. Okay, so I want to talk about, and I have a visual over here to the right. I'll show just briefly. There's two vectors. Those vectors, the purple one has length 4 and is going to stay fixed. The red vector, I've made it so I can click and move it around. There we go. I'm going to show one other thing here, which is, and I'll explain this in a second. I'm going to show a quick calculation here as I do this. So let's talk about the angle between them, and then let's talk about the dot product. I'll calculate both those and highlight that in my visual. Okay, so I have two vectors, u and v here. We're going to do their dot product. Right now it's positive, it's 3.8. Let's see what happens when I point the vectors the same way. The angle between them is 21 degrees, 8 degrees, 0 degrees. Ooh, we get 12. Now the purple vector was length 4. The red vector was length 3. So it turns out that when you two vectors point the same way, it's a normal multiplication. It's the multiplication of their lengths. So that's one reason we like to define this. It kind of does some things we want. So some people say the dot product measures how much vectors point the same way. And if they do point the same way, it's the product of their lengths. Now you could ask, what about the other side? What if they point the opposite way? Instead of getting 12, you get negative 12. You can see that. That's when the angle is 180. You also might notice it's negative when they point when it's an obtuse angle, and it's positive when it's an acute angle. Now the thing we usually use this the most for is when it's a 90-degree angle and it's 0. So if you want to think of perpendicular as they're not in the same direction at all, then the dot product is 0. Positive, the biggest it can be is when they point the same way, and it's just the product of their lengths. And if they point in an obtuse angle, away from each other, you get a negative. And the biggest negative you can get is when they're the opposite. So there's a visual of it. But it depends on the lengths themselves. That's why I can't tell you the number. Like I said, here it's 12 because their lengths are 4 and 3. Okay, hope that's sort of interesting. The same thing works in 3D. Okay, so let's get rid of that. And now let's do a little bit of proving. So every time you use this is how you'll use it. I didn't actually write down 10.3. I did write it down. So I was just thinking, I always give this proof, but the proof starts with the law of cosines. And so I thought, I never proved the law of cosines in class because it just takes a little too long. Because you can actually see the result sitting right here. So in some ways, the dot product is somehow related to that extra term. Now we're used to right triangles like this, and when it's right triangles, this is 90 degrees, and you get the Pythagorean theorem. If it's not a right triangle, then it's going to look something like this. And there's a theorem that relates that angle to the opposite side. Okay, so I started to think, well, how would I prove such a thing? And I'm going to show you what you would do. You would just collect all the facts you can think of. So it was a fun little exercise. I went through and I was like, oh, this is so fast. I don't know why I always avoid doing this, but it's not really something for class. Here's C, here's theta. Okay, so imagine you're trying to say something relating those three. And you can't use the Pythagorean theorem. So we draw a little line going down here. This is just from experience a little bit, that it's nice to work with right triangles. But the problem is now we don't know what this length is, and we don't know what this length is. So I thought, I'm going to label it x, and I'll label this b minus x, and I'll label this h. And then the strategy is to write down every equation you can think of. This is how I feel like textbooks often prove things in a clean way that don't show you how things are actually done. What's done is we label everything, we write down everything we know, and then we think of how to put them together. When we go to write a book, we don't show all that thinking. We just show the necessary pieces. Okay, so this is an exploration of how we think in math. So I'm trying to relate A, B, C, and theta. So I'd like to write down every equation that involves those. So first, I see a couple right triangles. And another one over here. I was in a high school class recently, and the teacher said, every time there's a right triangle, you should think there's at least one equation that goes with it. So my first thought is, hey, I got the Pythagorean theorem here. I can say x squared. And I don't know that this is the right thing to do. Again, I didn't look anything up. I'm sure there's a shorter proof, because once you've seen it all, then you can do it shorter. But that sort of hides the fact of how we think. I see another right triangle there, so I see, what would that be? I see b minus x squared plus h squared. And to me, this is what math is about. It's not about regurgitating. When you face a real problem, it's not going to fit perfectly. So it's about the thinking. Okay, I could see it. Maybe I can combine those. There's this unnecessary h and x in here I'd like to eventually get rid of. Is there anything else I can say? I would like to involve that angle theta. Well, there's 6 different trig functions, but I'd like ones that involve this a, and maybe the x, and maybe the h. So anyways, my thoughts are, how about cosine of theta is x over a? How about sine of theta is h over a. Tangent of theta is h over x. When I first did this, I didn't even write that one down because h and x were not links I was interested in. There probably is a way to do that. And it could be I don't even need all of these. In fact, I think I don't need all of these. But you notice I haven't allowed myself to panic yet. I've collected all the facts I could think of that relate my sides. And now I'm going to try to see if I can somehow say something about A, B, C, and theta. What can I say? See if you can put them together. Play that game yourself. Anyways, what I see is I have an h squared here, and I have an h squared here. So you can substitute. You could solve for h squared and substitute. Or if you want to be clever, you can subtract things side by side. Let's do that. Let's say we take the second equation and we subtract the first equation side by side. On the right, you then would have c squared minus a squared, which is kind of looking like I want. The h squareds would cancel, and on the other side, you'd have b minus x squared. So this is a standard thing you're going to be doing in this course and in all your math courses, which is putting together facts. Oh, that kind of jumps out at me that I want to do something with that. I really want to expand. Now, me, as a student, I always liked algebra, so I was like, all right, I'm not afraid to do a few lines and make it look better. I think some students have this loss of confidence where they think the algebra part is bad. The algebra part is usually the part that's just, once you're there, you've done the hard work. Okay, that looks a lot like what I'm trying to prove. In fact, let's get the c squared to the left. Let's move everything to the right. In fact, let's just think of this as the left and move everything to the right. So we're going to write c squared is a squared plus b squared minus 2bx. Well, we didn't want x, we wanted theta. What can we say about x? Oh, x is a times cosine of theta. And it really was enjoyable when I did this. I feel like I felt bad that I hadn't done it in so many years. I had only maybe seen this fact a few times ever, but I'd used it many times. And there's a real joy in just asking why things work. At some point along the way, somebody's like, hey, this basically tells me how much I deviate from a right triangle. If it's 0, it's a right triangle. If it's positive, it's an acute angle. If it's negative, it's an obtuse angle. So I don't know the order of the history here. I should look that up, but I suspect it's not known because it's such a prevalent operation we do. But maybe I'm wrong there too. That's the next time. But somebody's like, well, let's define the dot product of two vectors to be this thing. Probably this connection was already known. Giving it notation was the clever little thing. Okay, so this is, I think of this as intimately connected to the law of cosines. How much do we deviate from a right triangle? All right, the actual proof from there goes like this. I'm going to grab it from my notes. This is the proof I usually show students. I just don't usually give that preamble. So I tell students, assume you already can do this. Now, the thing we're saying here is that we have these two vectors A, we have another vector B, and we subtract. And when you subtract 2 points, or the ends of two vectors, you get a vector that goes from one point to the other. In my class, we call it a directed line segment. That's that. So it forms a triangle, and there's this angle between them. So it is the law of cosines we're talking about if you want to relate the links. Now, I talk in class about the fact that this is the same as the dot product of a vector with itself. That was one of our operations. We talked about how we can expand it out. So in my class, we talk about some of these things building up to this. But my students are not expected to know this proof. And then we talk about, well, that means this is the same as this. And then we subtract these from both sides, and what we're left with is -2 times the dot product is this thing from the law of cosines. So there you go. That's the explanation. There's several consequences of this, but I hope that gives you a feel for what dot products are and what they mean. For people in a vector calculus course, you just need to know you can compute it, It's quick. There's one real big application beyond this called projections, but I'll do a separate video on that. All right, hope that's interesting.